All right, in this video, we're going to be talking about a velocity selector. All right, so let me just draw the diagram first. So here you have got two plates connected to a power supply. So let's just say that's positive, and this one is negative. Now these are sort of sorted out for the moment. Now, where is the arrow pointing when it comes to the electric field? So if we were to put a positive test charge here, that's a positive test charge, the electric field is going this way. Okay, so that's the electric field. Now the magnetic field is going into the board. Okay, so the magnetic field is going into the board. If we use Fleming's left-hand rule, the force is going up. So the magnetic force is going up. And what's going down? The electric force. So here you've got the magnetic field there. And so the electric force is going down. Right, what is the equation for magnetic force? Now you could say that is equal to BQV. If you remember Bev, substitute E for Q. So F is equal to BQV. That's for magnetic force. And what about electric force? Well, the electric field strength is force per charge. So force is electric field strength times charge. Well, that should be, it's a velocity, isn't it? Okay, so the electric force is equal to you don't need that arrow on top of the Q. What are you doing? All right, so that's a Q there. All right, so now you can equate them. Now they will go in a straight line. Now, if you equate them, BQV is equal to EQ, the Q's cancel, and V is equal to E over B. Okay, so now what happens if V and E are certain values? So if E is 4 times 10 to the 5, so if E is 4 times 10 to the 5, let's just say it's volts per meter, and if B was 0.1 Tesla, then V is equal to that divided by that. So that divided by that will give you 4 times 10 to the 6. So only those with that speed will go in a straight line. Okay, so we're doing a video on mass spectrometer. Okay, so we're doing a video on the mass spectrometer. Now, okay, so the video is on the mass spectrometer. Okay, so what are the principles, or what are the procedures, what are the steps? So 1, it is ionized, and number 2, it gets accelerated through a potential difference. So potential difference, it will accelerate, and then the next stage is that it goes through a velocity selector. The fourth stage, after it goes through the velocity selector, it enters a region of uniform magnetic field. So uniform magnetic field. And part 5, different substances, different ions, they will have different radii. And then part 6, it goes through the detector, and then the computer analyzes the results. So number 1, it is ionized, or there's an ionized source of ions. Okay, so source of ions, potential difference, that makes it to accelerate, that makes it accelerate. It goes through the velocity selector, and then after the velocity selector there'll be a uniform magnetic field. Then because of the different masses, different radii will occur. It hits the detector, and then the computer analyzes. So let's just draw a quick diagram. All right, so this is the source. That's the source. It gets accelerated through a potential difference. So let's just say that you've got a voltage across here. Let's just say a voltage across there. Accelerates. Then it goes through a velocity selector. So this side is positive, this side is negative. So we covered this previously. So the electric field will go down, magnetic field is up. So when both are equal, it will travel in a straight line. And it comes out through another aperture. Here is the magnetic field, so uniform magnetic field. But it's also a vacuum chamber. All right, so depending on the mass, I'll explain why the equation. So here it will be heavier ions, and this one here will be lighter ions. Here is the detector. So this is the detector. And here is connected to a computer. So this is a computer. The detector is here. All right, so what are the equations? mv squared over r is equal to bev, or bqv. Now the v's cancel and we want r. So r is equal to mv over bq. Okay, so the bigger the mass, the bigger the radius, because r is proportional to m. So if m is massive, then r is massive. Okay, so here you've got heavier ions, so that means that the m is high, and so therefore r is high. All right. And the graph could look something like this. So your y-axis will be your abundance. So your y-axis is abundance. And your x-axis could be the nucleon number. So nucleon number. Okay, so on the y-axis, you've got the abundance, and on the x-axis, you've got the nucleon number. And you could have peaks. So that could be an example of a graph. Now, modern spectrometers are capable of identifying relative abundance as small as 1 in 10 to the 14 ions. So 1 in 10 to the 14 ions. Okay, we haven't covered why we use mass spectrometry. So we can use it to measure the mass and the relative concentrations of atoms and molecules. So we can use to measure mass and the abundance of atoms and molecules. Abundance of atoms or molecules. And is used for all kinds of chemical analysis. For example, examining pharmaceuticals and age of ancient rocks. Ancient rocks or pharmaceuticals. Okay.